Hello, Dr. Painter. I'll be presenting on the CDC's operational research project. What their main goal was to create a network of hubs in order to be able to disseminate a vaccine or a cure or to treat people in the case of a mass pandemic. The reason I chose this one is because obviously we are facing the same issues right now. Now, the only funny part I want to add on to that one is obviously they didn't calculate into the number of people that would deny were even in that pandemic. So now I'm sure that this model is slightly off just based on that information. After reading through the entire paper, I did not see anything taking that into account. Next, now the problem that was definitely being solved was planning for a catastrophe. Their goal was to mitigate the harm of a disease outbreak in the United States by creating systems for mass distribution, location of supply centers, optimal staffing, routing the population, and dispensing methods. So the reason that this problem came into the scope of the CDC was when they started running a lot of the tests and simulations. Many of the places that they tested did not even pass the minimum requirements that the CDC set in order to call it a proper response. And so these group of mathematicians, they were tasked with, creating a system that's easy to use that would tell the user how many hubs they should have, how they should stuff it, or how they should staff it. Also, on top of that, they talked about how they would disseminate the supplies and disseminate a vaccine. And what this does, it takes out a lot of the human error, and it saves a lot of staffing meeting time, and it makes it a direct and clear list of needs and people that you need in order to solve this problem. Now, before I get into the nitty-gritty of the equations and describing all the variables and constraints in the equation, I thought I should describe it in layman terms the best I could. Now, when looking through the problem, they were definitely facing the problem of allocating resources. So that's going to be your main constraint, are going to be your resources, which can be considered supplies and staffing. It also takes into account the traveling networks in each city. That ends up actually being a big constraint as well in order to determine the locations of these pods. Now, the biggest part of this is that it's really more of a simulation. So this is more of a heuristic. It's not going to be a perfect optimal solution every time. Although when they ran it, they were able to get a solution that was with 8% of optimality within 10 to 50 computing seconds. So this is a good algorithm in order to determine the best optimal solution, especially when responding quickly to a pandemic that you need to control right away. Now, in this simulation, their goal is to minimize labor costs along with the cost of system variances. Now, we're going to go into what system variances mean, but a lot of things that system variances will be like the wait times, the number of material they have, the docking doors can even be one, equipment, labor, and you can even subset labor into two other things. You have medical personnel versus non-medical personnel, because medical personnel are the only people that can take care of the vaccines. But then you have the non-medical personnel, which can be in charge of supplying water, supplying food, telling people which lines to stand in. There's a lot of things which go into determining the amount of people. They call it a throughput. Each pod can throughput. Now, like I said, our objective here is to minimize labor costs along with the cost of system variances. This falls into some certain constraints. Is going to be our healthcare personnel versus non-healthcare personnel, food and water, and do we need both to do so? So on top of that, we also have to take into account in smaller population areas, you can even use the medical personnel to also distribute things that non-medical personnel could have as well. And then lastly, we have our resources. Another thing they take into account is they have a max limit on wait time. They have a range at each station. They have assignability and availability of resource types. And then they have the max limit of a cycle of each person. Now, what the cycle of each person means is how long they're going to be working in that pod in order to make sure that their exposure rates stay down. Because if they become exposed, they then expose other people. So it becomes a whole circle. Now, what they did a wait time based local search, and it was based on a greedy local search. So I'm gonna go ahead and break this down into how the algorithm worked, and then I'm gonna get into the actual equations. So first step was it offers a warm start. What that means is it either starts with some people going already, or is it gonna be a cold start, as in open to the full public. Now, this depends on the user input. So the user has a lot of control over what the algorithm is actually looking for. And in this case, this is going to depend on the user inputs. The user wants a warm start. They can select warm start. If they want a cold start and just go full blast, serving the full population, they can do that as well. Now, these are based on a lot of different factors. These factors are queue lengths, a wait time, and combinations of those two. And there's also other factors that take place in this as well. Now, where this algorithm takes place is it's going to do a queue length based local search. So it's going to take the most efficient wait time and plug that in for a solution. And then it's going to compare the neighborhoods from there. And it's going to find the most optimal solution in each neighborhood. Now, the second step is you want to find, after you find a good optimal solution, you want to find your largest violators, and add resources to fix those violations. After you find the largest violations and fix them, you want to go ahead and rerun the algorithm again. But the part about this is it is sensitive to the order checked and the number of violated constraints. So if there are a lot more violated constraints, obviously you have a chance to, or the opportunity arises to miss the most optimal solution, because there's a possibility of so many different neighborhoods that you can't even get to. Next, and also if you check certain things first, obviously your solution is to fix that first, even though that might not be the most optimal. So that's the second step, is find the violated constraints and fix them. Third step is when all the constraints are satisfied, you need to be able to match the available skill pool in order to sufficiently serve the population that's going to come through there. So that's when it comes into account. You have to take account for your medical personnel, your non-medical personnel, and your transportation networks in that area. Next, after you do all that, after you've matched your skill pool and allocated resources on where they need to go, the last thing is you want to simulate it one more time and then report your results. Now, after the fourth step, what we're looking to maximize the throughputs while also limiting the number of infections. So basically, we're just trying to serve the most number of people and stopping infection from happening from people within the pod and also even the general population, which I'm going to dig into when I dig into the numbers. So now I am going to break down what the actual equations that the people at the CDC created. This is going to be talking about what each of these things mean. Now we have S, E, P, A, I, R, and D. Those are our main variables that we're working with here. These are representing sets of the population. So S are your susceptible people, E are your exposed people, P are your infectious people, A are your asymptomatic, I are the symptomatic, and R is the recovered, with D representing the amount of people who have died from this. Now, we have some constants involved with this as well. So we're going to go ahead and start from the top. This symbol right here stands for the patient arrival rate. And so this means the opposite of the patient arrival rate times the percentage of the population that's susceptible, or the decimal point. So the percentage of people that are susceptible. You're going to subtract that. You're going to subtract the minimum of, well, n of 0. This right here is still standing for the population we have, where this symbol here means the average number of contacts. So this, you take the minimum of that, so which one's less, and then we're going to multiply it by the average transmissions per contact times, well, P are the people, all the people that can spread it. So you have the infectious people, the asymptomatic people, and the symptomatic people times, once again, the percentage of the population that's susceptible. So that's what this first part means. And then that makes sense because that is how the susceptible population is changing, where this 0 stands for the, go back to that. This 0 stands for the number of outer pod individuals at the stage V of the disease, where the stage V of the disease is a subset of our original set of SEPAIR, D, and V, which V stands for vaccinated. That is our set. Now, this number right here represents whatever stage they are at the disease. So you can either be susceptible, you can either be exposed, infectious, all those good stuff. So that's all of these things times the percentage of the population that's susceptible. Now, the same thing is going on here. They are talking about the rate of change. The rate of change here, which makes sense that we're multiplying by the average transmissions per contact. We're trying to get an estimate in order to make sure our pods are serviced. So all these equations all have the same general meaning. Now, the other constants we need to talk about are going to be this constant right here, which stands for the rate from people moving from the infectious to the symptomatic, is this right here. And this rate right here is the UI times U of A. So where is that? There's the UI times this is worth the is the rate from symptomatic to recovered. So it's the people becoming better, which makes sense because we want to get people out of this category and we want to get people out of this category in order to get them into recovered. So it doesn't matter whether or not they're asymptomatic or they were symptomatic. Our goal is to get them in to RO, which that rate can be symbolized by this or this one. Now, once again, talking about this, these all stand for the rate of change of those populations. And these are the constraints the computer takes into play when it's running its algorithm. Okay, so I'm going to be looking at this next set of equations. That first set of equations represented the population outside the pod. So it's important to know that because we want to make that population smaller and smaller. But then we also really need to care about the population inside the pod because that is the whole goal. We want to get people in and out as quickly as possible in order to serve the most amount of people possible. Now, where this comes into play is this. So once again, we still have the susceptible population. We still have SEPAIR and D. Now, what's going to happen is I'm going to break down, the equations were too long to fit into one screen where it was actually visible. So I'm going to break it down to two different sections. So right here, we have the rate of change of the susceptible population inside of the pod. Now, this SI, the I is actually whatever station number we are at. And then this is equal, well, this right here represents a binary variable. So if this is equal to 1, the only thing that means is that it's the very first station in the iteration. Now, this is times what we have as the patient arrival rate. So this is the amount of people that are arriving at station 1 times the percentage of people that are susceptible, because once again, this all only matters because we care about the different populations. You want to make sure it adds up to the total population. Now, we're also adding the sum right here of 1 minus this symbol right here, which represents JI, which J is the station and I is the downstream station from that. So what this means is going from station J to I, that is this variable right here. This one represents the transition percentage, so the amount of people going from one station to another, where this symbol right here can be interpreted as the real service rate for individuals at disease stage V. So this is the number of people that are being serviced at each stage at station I. So no matter, this kind of takes into account the fact that they have mixing of people at different stages. That's what this variable does. And here we go. And then once again, this variable right here still represents the average transmissions per contact. Well, this is also the reason that we're multiplying by P, A, and I are because these are the people that can actually pass on the disease. And then once again, we're still multiplying by the people at that station. So these are all the people that are infectious at that station times the number of susceptible people that are there. The reason it doesn't matter for P, A, and I is because they already have the disease. Also, the reason that R, D, and V are not included in this is because of the fact that either R stands for recovered, so theoretically they would have antibodies to protect themselves. D is dead, so that explains itself. And V, they're vaccinated, so theoretically they also cannot catch the disease again. And this is the rate of change of our susceptible people. So these are the susceptible people, and these are taking away all the people that got it, essentially. Now, this right here is the rate of the exposed people, so we don't know if they're going one way or the other. These all stand for the same thing, and the same idea applies here. Now, the difference is we're not going to be subtracting the downstream station here, whereas this right here still stands for the people transitioning, whereas H stands for the people that are being serviced there. So those things matter because they still have contact. People that are transitioning and people that are being served, they still have contact within each other. And once again, this E is our exposed population, where now this is this stands for the rate from exposed stage to infectious stage. So this is the rate at which those are changing, which makes sense if it's multiplied by the exposed population, because the percentage of people that go from exposed to infectious is going to be the change from E to I to either P, A, or I, which now becomes a possible infector of the susceptible population. And once again, this symbol still stands for the average transmissions per contact, because these people that are exposed are not necessarily guaranteed to get it. So it still matters at the rate at which they're exposed, because the second exposure could truly be the thing that gives them the disease. Now, once again, all this stuff right here, the P is going to stand for the infectious crowd. So now we care about where the infectious crowd are at. This one right here stands for the rate from infectious to symptomatic. So whenever you go from, because you can be infected without giving it to people, but you can't see that you have it yet. So you can still transmit it while you are sick without knowing that you're sick. And then this right here still stands for the rate of people moving from exposed to infectious. And then the same, without loss of generality, the same stuff applies for all these other algorithms and equations as well. Now, V is vaccinated. Now, these are the people that are going through the stations. And now this is where the biggest change in the population occurs. This right here is taking into account that they're downstream from each other and they have to go through every single station in order to become inoculated from the virus. This S still stands for the susceptible population and each iteration. And you're going to add it to the number of people that were serviced and subtracting it from the number of people that are at disease stage at each station I. So if they already at a disease stage, it means they already have it, so the vaccination is not helpful. All right, so that is my general understanding of how these equations worked and what each part of these equations mean. Okay, the last thing I want to talk about is how this was implemented. This was implemented in order to create an easy-to-use system for city managers and healthcare officials to implement in cities in the case of an outbreak. Now, what they did after they ran these, created a program. It's like a 7-part program where they determine where the pods are at and like how they're how effective they are versus the population they serve versus the network systems. And it was a 7-part thing, but it does it nice and easy where it tells you every single thing you need to know. Now, the reason that these equations were important for that was because we're trying to make sure that we serve the most amount of people possible with the least amount of resources. Now, the result of this project was this. They had a lot of, after they created this program for people to use, they had an opportunity to field test it in real life. They immediately implemented it after the field test because they were able to see the effectiveness of this. They served more population with less resources using the RealOps system. Some examples of this are in Site 1, serving a population of around 700,000 people when the H1N1 vaccine was being dispersed. They only used 28% of the amount of staff they had previously used when distributing this H1N1 vaccine. Now, the reason that this is important is because it saves resources, saves people, saves time, saves money. Also, the throughput ratio, which basically is saying the amount of people it served. So with only 28% of the staff, they served 466% more than the people did not using RealOpt. Some other examples of this in the largest population that it served, which was 4 million people. There's a Site 11, and it was serving 4 million people, and this was distributing oral antibiotics. They only had to use 44% of their population, or 44% of the original amount of staffing that they used in the control trial. Whereas after that, they still served 2.79 times more people using only 44% of the staffing from the control trial. Those are some pretty significant results. The most significant result I see on here is this one. In a population of 1.44 million people, they only used 15% of the original staff and served 10.1 times more people. So the results and the effectiveness of this RealPod program being used is seen out there every single day. And especially with this whole pandemic thing going on right now, this is an important thing for me to look at. I really enjoyed looking at this project, and I thought it was very, very interesting how people are able to use optimization problems in order to solve a problem like that. I thought it was very neat to really dig into how we set up set sizes and how we quantify it. I thought it was very interesting. It was something I would have not thought to segregate the populations into SEPAIR and D and V for vaccinated. it makes a lot of sense when you really think about it, because that covers most people. You're either vaccinated or you're not. You're dead or you're alive. And then all the other levels of it covers every other level of the stage of infection you can be. So overall, I thought this project was really neat. And I thought the CDC did a really good job in taking a program and making it user-friendly and thoroughly improving the response to a national health crisis.